for the introduction. Okay, it's my last last one. Looking forward. And it's actually, maybe it's also the easiest to digest because it's about kind of classical physics. It's not about drift, diffusion, excitons, and so on. It's more like Ohm's law of current that we're looking into. And yeah, so title is Design and Optimization of Large Area OLEDs by Electro-Thermal Modeling. But I have to realize that it's mainly about electrical modeling. The thermal part of this is still under development, I have to admit. The next version of this software will also include the thermal coupling, meaning where you have lots of current density, there will be heat generated, and then the heat can either transfer to the air or radiate, and so on. So it's mainly about electrical modeling. The colleagues that are working on this, Roman Hirstand is the software engineer that implements this Laos software, Stefan Altazan, Christoph Kirsch, and other colleagues here that help to put in the right physics and also to test it and document everything. So the content of this presentation, I will try to motivate. Why should we care about large area device simulation? And then, I'll give you some examples from OLED lighting. First examples are OLED lighting panels, so the OLED will be 1 pixel but very large. And then the next case study is AM-OLED pixel crosstalk. This is something very recent that we have applied. We have applied this software also to study pixel crosstalk. If you have high resolution AM-OLED display, then there can be a challenge that if the pixels are too close to each other, that they can influence each other. So this is another case study. And if we have time left, I can also explain a bit how is this kind of software, how can you use it, how does it look like. Okay. Yeah, so we're talking about this little baby here. It's not even 1-year-old baby. It was released last August. But it's now already version 1.2. So motivation. As you work in a research lab, you're mainly dealing with small pixels, small, maybe 2 millimeter square OLEDs, or a few 4 millimeter square. And then in terms of electrical behavior, it's usually sufficient to just do one-dimensional electrical modeling, so across the layer stack. And this is what I have talked about yesterday, like impedance spectroscopy and so on, repeat measurements after periods of stressing, and also study light-out coupling. But now, as you go on with upscaling the device to multiple centimeters square, there are additional issues you have to care about. Namely, for the application, you want to have uniform brightness. And in order to achieve uniform brightness, you have to make sure that the potential drop between top and bottom electrode is the same all across the large area OLED panel. And this can be a problem if the transparent electrode, usually the high transparency means that there's maybe limited electrical conductivity. So this trade-off between transparency and electrical conductivity gives rise to some potential drop. So if you want to have good transparency, ITO for instance, the more transparent, the less electrically conductive. So you will end up with some potential drop that the applied voltage at the boundary of the OLED panel is not present in the center of the OLED, where you already have less applied voltage than at the boundary. So the sheet resistivity is something we have to worry about. And after all, the last thing is the thermal management. Typically, if you have a square or rectangle OLED, you collect the current at the edges. And so all the current has to flow from center to edge. So it means that the boundary along the large panel, you have the highest current density. And that's also where you have the highest heat generation at the boundary of the large area OLEDs. And if you have high temperature rise, then, as you know, temperature is an acceleration factor for degradation. So you can even end up with an OLED panel that at the beginning it is bright at the edges due to inhomogeneity, even for the fresh panel. But then if the heat is high at the boundary, that's where you have more degradation. And then the OLED panel also has an inhomogeneous degradation that you have. The OLED gets worse at the boundary. And so this could be all a motivation to do modeling, electrical and also thermal modeling. Now, I mentioned that, you know, the potential drop, we want to operate the OLED at a certain brightness level, so we need to have a certain current density. And usually with these thin OLEDs, doped layers and so on, you have quite steep IV curves. So if you have different locations along the OLED panel, and if there is resistive losses, then you end up with a different voltage, so a slightly different voltage due to the steep IV curve. You end up with a strong inhomogeneity in brightness, because if there's too much resistive losses in the transparent electrode, then the operating point will move and you have less brightness in that area, especially in the central area. So typically you get less brightness in the center of the large OLED panel, but more brightness along the edges of the OLED panel, because there you have less distance between the OLED and the boundary of the frame. Okay, so that's the reason why most OLED lighting panels, they do have additional metal grids. I think this example is from Osram, Regensburg. I'm not sure if they sell this type exactly like this, but it's a nice example where they have added this hexagonal metal mesh on top of the transparent electrode to make sure that you have better electrical conductivity from the boundary to the center, meaning that you end up with the same voltage potential difference in the center as in the boundary, so you can get homogeneous brightness. So these three examples are OLED examples. You already see this little window here shows you that in our software you can select a metal grid pattern. You can choose, I want to apply a hexagonal metal grid, and then in the end you get a potential distribution. So the boundary here, the red points at the boundary, they would represent the applied voltage. I'm sorry, the scale is missing. So it looks, in this picture, it looks very inhomogeneous, even though we apply the hexagonal grid. But if we would have a scale to read, we would probably see that blue is not much different than red in this case. So I'm sorry, the scale is missing, but we can have a live demo of this calculation at the end and we can check. So nevertheless, even though you add the metal grid, you still have a small change of potential from boundary to the center of the OLED panel. And then another motivation for us to develop this software was to also study solar cells. On the bottom left, you see two examples of solar cells. One solar cell has a high fill factor, so more power generated. That's the dark blue. And the maybe I have to read the legend. Yeah, the blue. So what, I should be more specific. The blue curve is a solar cell that has a small area, just a few millimeters square. And the green curve is a solar cell that was upscaled to several centimeters square. And that's exactly what we want to study there, to help the upscaling process. A lot of times record solar cell efficiencies in the lab are nice, high values, but if they scale it up even to 1 centimeter square instead of a few millimeters square, the solar cell already will have less power, less fill factor, so it will look like a green one. So that the larger solar cell will be the green curve, and the very small solar cell will be the dark blue curve. And our software, what's the recipe? What we suggest is to, if you have a solar cell, a small one in the lab, you can measure the IV curve, and you take this current density versus voltage, this IV curve, you take it in, you import it into the Laos software, and that's exactly the blue curve. And then Laos does the calculation for the large area solar cell, and you get the green curve. So the green curve is not as good as the blue curve, and so you can see the difference because of the potential drop in the electrode of the solar cell. You will also have less power extracted, because the solar cell also needs a potential drop between the two electrodes to pull out the photon carriers. Okay, so there's also an upscaling issue, and then there's even a design issue. If you want to, if you think of OPVs or solar cells that maybe are used indoors, they should look nice, and then you can design solar cell modules with, for instance, 10 solar cells connected in series with a funny shape, and then you want to make sure that each solar cell provides the same current because it's serially connected. You should have the same current everywhere, and so you need to design the area of each individual solar cell to have the best performance. Okay, back to OLED. Again, I show you this picture of the peeled off LG Chem white OLED panel, where you could maybe recognize still these rectangular metal grid lines that you see here, that are there because otherwise the potential would not be uniform. The electrical potential would be non-uniform, so it is an example that this is needed. And in terms of temperature, I mentioned at the beginning, this is a real measurement that was taken with an OLED panel. In terms of temperature rise, we see that on the left picture we have a temperature map in operation, and then a luminance map. So as I mentioned before, typically the electrical potential drop from the boundary to the center will lead to a smaller applied voltage in the center. That's why the boundary will be more bright than the center of the OLED panel. And where you have a lot of brightness, it's a sign of high current density. So at the boundary, high luminance means high current density, means also increased temperature rise. Okay, now the first simulation example, a quadratic OLED of 10 by, I think 10 by 10 centimeters, operated at 6 volts with a kind of moderate, poor ITO conductivity, and we see a significant inhomogeneity. So the scale you see on the right applies for both pictures. So this one also, if we see the boundary values is 6 volts, but the dark blue here shows that we only have 5.1 volts in the center of the OLED. And remember the steep IV curve, it probably means that you will have less current density and less brightness in the center. Now what's the difference on the right? The same OLED stack, but on the right we have added a metal grid, and I think it's quadratic. You can slightly see a quadratic pattern here, but it's almost invisible because the potential is now much more uniform. This orange means that we only have boundary values of 6 volts, and in the center maybe 5.8 or 9. So it's much more uniform potential distribution that would suggest more uniform brightness in the OLED. Now there has been previous experimental work by the NATES group. They have already measured the brightness across such an OLED panel, and in this case I think it was 3.5 volts applied, and then what we did here, we added our simulation result, and for simplicity what we did, we just calculated current density into a luminance in order to be able to compare with the measured luminance. And so the shape that we get here is very much the same as in that experiment. So that's the inhomogeneous case without any metal grid, but if you would add a metal grid, you would get much more uniform distribution. And here's an example, a different one. This one is again a square shape OLED, but this time the voltage is only applied on the up, left, and bottom side, but not on the right-hand side. So that's why it looks a bit funny. So we do get the potential that we apply at the edge on the left. So this point here on the left, that's where we have the applied voltage. But then if we don't use any metal grid, the potential will drop strongly as we go from boundary to the right-hand side here. And then if we add a grid, then we get this potential profile in red. You see the little bumps here that are due to this metals. So yeah, it behaves nicely. Now we have a more uniform potential across the OLED, and it will be more homogeneous light emission. Yeah, you can play around. Of course, here we had vertical and horizontal metal lines. But if you would start out with the green case here, so this is a current voltage curve of the OLED panel. The green curve is without any metal grid. Then if you add the, what is it, 1D aluminum grid and 2D aluminum grid. So blue means just in one direction metal grid, and purple means in horizontal and vertical direction a metal grid. And you see that for an applied voltage at the boundary, you get more and more current because the uniformity of the potential is better, and therefore the OLED draws more current. So you have more current at the same voltage. And the red curve, what is the red curve? It's basically that's the theoretical limit. That's the best current we could get for a given voltage, because in this particular simulation we have assumed that the OLED has a quadratic Mott-Gurney law, so the current scales with the square of the voltage. And so for a very small OLED pixel, this would be the maximum current you could get, but because the OLED has a finite size, it's larger, this is why we get less current for a given voltage. But or in other words, of course, you can also cut horizontally, meaning if you're interested in a certain brightness or a certain current density, you would have to apply more voltage to achieve the same current because you have the resistive losses. Okay, so all these calculations, it's always good to compare with a reference, and here the reference is a small device, only 1 millimeter square, for instance. That would be the best JV curve you could get, and all the other cases are worse than the red one, right? Okay, that was the OLED lighting example. Now I would like to show you that this is also useful modeling method for pixels, small pixels with crosstalk. We have seen this nice study in a conference in Korea where LG Display has discussed at this poster the influence of common HDL layers. So you see here a cross-section of a red pixel and a blue pixel, and they share a common Hall transport layer which goes across the two pixels. This is for ease of fabrication. You don't have to pattern necessarily this layer, but because there is some conductivity in this doped, it's a p-doped HDL layer. So as a result of this, if you turn on one pixel, this blue one for instance, you still get some light output in the red pixel because the potential of this blue pixel somehow leaks over to the red pixel. And this is a problem if you think of OLED display not only for mobile devices, but the pixel resolution will still go further up because you'll have virtual reality. You need a very high resolution in front of your eyes for VR applications. That's why it is an issue. And what they studied here in the poster is also a variation of the p-doping concentration. because if the p doping concentration is too high, then it gets more conductive and the problem gets even worse. But that's another aspect. So what we did is just to generate a similar example. We looked up just an old pattern, a layout of AMOLED pixels as it has been used. This is a real picture on the left, and in the middle we have a drawing that we try to reproduce this pattern. So there's an elongated blue pixel, and then there's a red one and a green one. We assumed these dimensions, which are consistent with the given PPI. I don't remember how many pixels per inch, but and this on the right-hand side, you see the CAD drawing of the same pixel layout in the Laos software. And then we will apply a voltage only in the center blue pixel, and we will check how are the neighboring pixels affected. And so we turn on this, it's this. It has a red frame, but it's a blue pixel. Yeah, a bit confusing. We remember, I mean, this is elongated one is the blue pixel. So this one is turned on, and we run a simulation, vary the voltage in the blue pixel, and measure, meaning we simulate in the software, the current that flows through the red pixel, and also the green one. And what you see here, this crosstalk problem actually shows up only at low light levels. If the voltage is high enough, then you see that the brightness of the blue pixel dominates, and it doesn't matter that there is some remaining green and red emission. So the problem really arises if you have a low light level from the image that you want to display, and then there can be even more light from the neighbor pixel than from the center pixel. Yeah. Okay. So this is how it looks like if you plot the electrode potential. So the central pixel has the potential you want. It was 4 volts, I think, in this case. And you see from the color map that the neighboring pixels will also have, dark blue values means smaller potential, but still significant potential to give rise to some light of the neighbor pixels. And on the right-hand side, the resulting current in the vertical direction, so meaning between the two electrodes, the current flowing through the pixel is illustrated on the right graph here. We call it source current density. So the main current flows through that pixel, but the neighboring currents also have some current flow. And then the question is, well, of course you can then play around to optimize, change the conductivity of the common HDL layer, or change the separation, the distance between the pixels, or, for instance. So we quantified here a relative intensity here. The black curve just shows the ratio. How much light do we get from the neighbor pixel rather than from the central pixel? So at low voltage this is significant. So this is a problem. Okay, that was the first example of a display simulation, pixel simulation with crosstalk. Now you may wonder what is in this software, how does it work, what's the physical assumptions and what are the equations. So I will briefly maybe try to explain what the model assumes. The benefits come first, but this is more marketing, but easy to use. Get started quickly, don't have to worry about FEM algorithm because it's taken care of in the software. Yes, we all know that. Okay, physics. What do we do? Instead of simulating in 3-dimension the whole volume between the electrodes, we actually simplify the problem a bit in order to have a quick simulation result, and we don't want to wait for hours to get the result. And the fact is that these OLED panels are much wider than thick. So we can exploit this aspect ratio and decide just to simulate the top electrode domain as well as the bottom electrode domain and the semiconductor layers that build the OLED in between, they will be just described by a local JV curve, a local current density voltage curve, which couple the two domains. And in each domain, we are solving the continuation, the conservation law for current, so that's Ohm's law, and we can solve for the potential and evaluate the currents. So as an input, you will always need the coupling law. So you need to decide what kind of device do you have. Is it a steep IV curve or a small device? Then you can enter it here. And in terms of the equations, we have the conservation. The continuity equation basically means here, it's over here. Now this is Ohm's law. It expresses that the conductivity links the gradient of the potential with the resulting current. So that's Ohm's law. And this is the conservation law that we want to solve. Namely, usually you have divergence of J equals 0, but because we have a vertical current coming from the OLED into the electrode domain, the right-hand side of this equation is the small j, which describes the vertical current flow. So we have a coupling of a vertical flow and the horizontal flow, and the coupling is through this equation. And so we enter the Ohm's law for the current expression, so it's a drift current. We enter it on the left here. We end up with Poisson, twice the derivative in space. And on the right-hand side, we have the source term for the vertical coupling. And to solve this equation, we're using a FEM methodology, where the desired solution of the psi function here for the potential can be approximated by a superposition of shape functions, and these hi are so-called shape functions, and the psi I are the linear coefficients that you need to do this approximation. And then you can do the math, and in the end, you define actually how well is the solution. The solution is good if indeed the left-hand side is equal to the right-hand side. So you can make kind of you take the difference of the two terms, and if R, this residuum, if it is small, then it means the solution is good enough, or the user can define how well the equation has to be solved. That's called the residuum. Because in general, there's no analytical solution. That's why we have to do a numerical simulation. Okay, so the algorithm will adapt these coefficients psi I, so these weights of this superposition, such that the residuum will become small. And then this coupling law, the small j, the coupling law, in a previous example I mentioned we can assume Mott-Gurney law as quadratic behavior, which is a typical for space charge limited current in organic semiconductors. And then there are other options like a diode model, or simply an ohmic law. If you have, for instance, you can assume if there's a defect, a shunt, highly conductive point that connects two domains, it will probably behave like an ohmic conductivity. So this is what you can locally define, if you like, to study the influence of shunts. And you can also just import the tabulated current voltage curve, and that you measured in the lab. And then, so typical workflow, and this example of workflow refers to a solar cell example. We start with the layout. This is actually an organic PV solar module where there are several leaves. I think there are about 7 leaves serially connected. And you notice the black lines, these are actually metal current conducting metal grids. In this case, we just took one leaf. We wanted to simulate one leaf. We have imported the drawing file, a DXF of the geometry, that this CSEM is a research center in Switzerland. They have actually printed this solar cell on flexible substrate. So we took the shape of this cell. Then, so this is imported the CAD drawing file is imported into LAOS software, then you have to run meshing, meaning that this two-dimensional electrode domain is divided in small triangles, and then you have to import a current voltage curve that represents the solar cell under illumination, and then you can run the simulation and you get a potential distribution here for this particular shape and this particular applied voltage. And then you can, of course, iterate and change the geometry or change the material property, like the conductivity in this, this gray area. This is the transparent electrode. You can change the conductivity. You can iterate, change the layout, and so on. And for certain shapes or simple shapes, like rectangles or metal fingers placed on top solar cell, we have a parameterized geometry, so you can simply sweep parameters to see, to optimize the performance of the solar cell. But yeah, these are some examples of geometry inputs. So the simple rectangles, but then the metal finger, this one is popular in thin film solar cells. This finger here, it means we have an elongated cell, but across the direction of current we have a metal finger to enhance the current collection. So usually it's wise to just select a small element of symmetry of your problem. So because if you have many of such fingers, so in reality people use a comb of such fingers to have a current enhancement, and it's not needed to simulate the complete solar cell. You can also just look at one element of symmetry and do the calculation there, and you will be even faster. That's one example. And then here is another example where we have the user can specify the number of metal lines applied here in vertical or horizontal direction, and the honeycomb pattern is also available. And if you're not happy with the choices of geometries here, you remember that you can also import the DXF files. The DXF is a typical file format for CAD drawing, and actually you could use your own CAD software, like LibreCAD is a freeware software for two-dimensional drawings. So you can draw your OLED shape with a CAD drawing tool, and then just make sure these things are connected, these lines, and then name some subdomains here. There is only a few rules you have to follow, some LAOS naming conventions. If you follow the naming conventions, then this DXF file can be imported into LAOS, and then you can start with the simulation. So this is existing freeware software, so we didn't reinvent the wheel, but rely on other tools. And so after you have imported the geometry, you can start a meshing, and I will give a live demo just after. And this is the mesh. Then you define what's the local current voltage curve that couples top and bottom domain. And finally, the result will be a potential distribution, but you can also study the profiles of these calculated quantities. And if you're impatient and want to even have an even faster simulation, instead of solving two domains, you could choose only to solve one domain, and the bottom domain just assume that it's equipotential. In most OLEDs, you only have one transparent electrode, and the other electrode is anyway a metal, a highly conductive metal, and it's a good approximation to just assume that the rear electrode is highly conductive, so you don't have to solve that domain, only have to solve the domain here, which is transparent. Okay, and then there's a post-processing. Yeah, you can visualize cross-sections of the potential in the OLED for different, in this case, for different boundary values of applied voltage. And again here, the final OLED current of the large area OLED would be the purple one. The total device current is the purple curve. And the reference curve, which is called the local JV, that's the ideal current that you would get. So we can compare this if we look at the current densities, current divided by area. Then we can compare the small OLED to the large OLED, right? Otherwise, you would have different values for the. So that's why it's interesting to compare these two. Okay, the conclusion of this overview presentation is we introduce a new software for modeling solar cells and OLEDs. It allows to simulate, it allows to design the layout of electrodes with or without current enhancing metal lines. And you can play around with fancy shapes, import different shapes, and so on. And if you